Hello friends, welcome to my channel. This is Fluid Mechanics Part 14 Isro question paper from 2006 to 2016. For the stability of a floating body under the influence of gravity alone, which of the following is true? This one already discussed 2-3 times. MGB Meta center, center of gravity and center of buoyancy. So from option, meta center should be below the center of gravity, no. B, meta center should be above center of gravity for stability of floating body. B is our answer. Meta center and center of gravity must lie on the same horizontal line. This is for neutral equilibrium. A smooth pipe of diameter 200 mm carries water. The pressure in the pipe at section S1, elevation 10 meter is 50 kilopascal. At section S2, elevation 12 meter, the pressure is 20 kPa and velocity is 2 meter per second. Density of water is 1000 kg per meter cube and acceleration due to gravity is 9.8 meter per second square. Which of the following is true? So here we will apply Bernoulli's equation. Pipe of diameter, same diameter, so D equal to 200 mm equal to D1 to D2. Section 1 elevation is Z1 10 meter, P1 pressure is 50 into 10 to power 3 Newton per meter square. At S2, elevation Z2 is 12 meter, pressure P2 is 20 into 10 to power 3 Pascal or Newton per meter square. Velocity V2, same diameter, so A1 V1 equal to A2 V2, so V2 equal to V1 equal to 2 meter per second. Density of water rho given 1000 kg per meter cube. G value 9.8 meter per second square. Which of following is true? Flow from which section to which section? So we have to calculate in both points total energy. Total energy at one point is P1 by rho g plus V1 square by 2g plus Z1. So 50 into 10 to power 3 divided by 10 to power 3 into 9.8. V given as 2 meter per second, 2 square 4 into 9.8, 4 by 2 into 9.8. Z1 given 10. So it will come around 5. Here it will come 20 by 4. So around 0.2 plus 10. So 15.2 meter of water. Total energy at 2, it's P2 by rho g plus V2 square by 2g plus Z2. Put the values. P2 is 20 into 10 to the power 3 divided by 10 to the power 3 to 9.8 plus B is same 4 by 2 into 9.8 plus 12. So it will come around 2 plus 0.2 plus it's 14.2. So total energy at 1 is greater than total energy at 2. So total energy at 1 equal to T2 plus head loss due to head loss may be due to other factors also. So this is total head loss or simply head loss. So from option the flow will be from S1 to S2. Head loss also we have to calculate. So flow will be from S1 to S2. B not possible, D also not possible. Head loss, its head loss is total energy at 1 15.2 minus it's around 1 meter. So from option A not possible, C is our answer. The two dimensional flow with velocity which is B equal to x plus 2y plus 2, this is I cap and here j cap plus 4 minus y, j cap is compressible and irrotational we have to check. This one already discussed. So for compressible del dot V is 0 and for irrotational del cross V equal to 0. Here divergence, here curl. So in this question u equal to x plus 2y plus 2 and v equal to 4 minus y. So we have to check divergence and curl for compressible and irrotational. So first we will check del dot v. So del by del x I cap plus del by del y j cap plus del by del z k cap dot x plus 2y plus 2 I cap plus 4 minus y j cap. So we'll get 1 then del by del y j cap into 4 minus y j cap. So here minus 1 will get. So 1 minus 1 is 0. So it's incompressible. So from here A and B not possible. From C and D we have to check irrotationality. For irrotationality we have to check curl of V vector. Plus del by del x j cap plus del y del y del z k cap cross v vector is ui cap plus vj cap wk cap. So del cross b or call of b is ijk del y del x del y del y del y del z. U value given x plus 2y plus 2 and v is 4 minus y to 0. So I cap into del y 0 minus del y del z 4 minus y minus j cap into del y del x 0 minus del y del z x plus 2y plus 2. Then k cap into del y del x 4 minus y minus del y del y x plus 2y plus 2. So 0 minus 0 minus j cap into 0 minus 0 plus k cap into 0 minus 2. So it's minus 2 k cap, which is not equal to 0. So not irrotational. From option we have to check. Already two options we omitted, so this is not irrotational. So only D left, incompressible and not irrotational. A venturi of 200 mm throat diameter is used to measure the velocity of water in a horizontal pipe of 40 mm diameter. If the pressure difference between the pipe and throat section is found to be 30 kilopascal, then neglecting frictional losses, the flow velocity is how much? Flow velocity we have to calculate. So data given are 40 mm and D2 throat diameter is 20 mm. Pressure difference is P1 minus P2 30 kilopascal or 30 into 10 power 3 Newton per meter square. Flow velocity we have to calculate. So Bernoulli's equation, first from continuity equation we have to calculate V1 and V2 relation. So A1 V1 equal to A2 V2 pi by 4. A1 is 40 pi by 4. D1 is 40 square into V1 equal to pi by 4 20 square into V2. Pi by 4 cancel. So it's 4 V1 equal to V2. This is relation between V1 and V2. Then we have to go for Bernoulli's equation. P1 by rho g plus B1 square by 2g plus Z1 equal to P2 by rho g plus V2 square by 2g plus Z2. Z1 Z2 cancel. Then G also cancel. So P1 minus P2 by rho equal to V2 and V1 already we got 4V1 square minus V2 V2 is 4V1 square minus V1 square by 2. So it's 15 V1 square by 2. So we got P1 minus P2 by rho equal to 15 V1 square by 2. So V1 square equal to 2 into P1 minus P2 by rho. V1 equal to root over, we have to do 2 into 30 into 10 to the power 3 divided by 10 to the power 3. Here it's 2 by 15. So 15 here, 10 to the power 10 3, 15 into 2. So V1 equal to 4 root over is 2 meter per second. So from option D is 2.0 meter per second. D is our answer. In case of steady incompressible laminar viscous flow between two stationary parallel plates, the velocity distribution is how much? Two stationary parallel plates. The velocity distribution, shape of the velocity distribution like this. See, T, gap between the plates, direction is Y. Velocity distribution is parabolic. And three things are important here. Sometimes they are asking in list 1 and list 2. Flow inside a pipe, which is Eigenpauli equation, and between two fixed plates. Then one plate fixed, other is moving. This is Curtis flow. In pipe it's Eigenpauli flow, and in case of two plates are fixed, it's forceless flow. And one plate is fixed and other is moving, then it's Curtis flow. These three things are important for IAS examination, ISRO, and GATE examination also. In GATE examination, from Eigenpauli equation, so many times they asked the problems. And for IAS examination, in case of two fixed plates, forceless flow, three more formulas are important. For U, it's 1 by 2 mu into del P by del X to Ty minus Y square. T is the gap between two plates. Y is distance from lower plate. Direction is from bottom to towards top. And here U average or average velocity is 2/3 U maximum, and U maximum is T square by 8 mu minus del P by del X. So many times asked in IAS examination, these three formulas. Sometimes for conventional papers also they may ask this type of questions. You have to use these three formulas. Two pipelines of equal length are connected in series. The diameter of second pipe is 2 times that of first pipe. The ratio of head loss between first and second pipe is how much? Connected in series, or pipes are series. So D1 is due second pipe, it's 2. So D2 is 2D, and we have to calculate the relation HF1 by HF2. Series case, so Q1 equal to Q2. HF formula also we already discussed, FLB square by 2GD or FLQ square by 12D to the power 5. So pipes are equal length, so L1 equal to L2. We have to calculate the relation between head loss between first and head loss by. So HF1 by HF2, F1 L1 Q1 square by 12 D1 to the power 5 divided by F2 L2 Q2 square by 12 D2 to the power 5. Friction factor both case same, L1 equal to L2, Q also same, 12 cancel. So D2 by D1 whole to the power 5. D2 is 2D, D1 is D whole to the power 5. 2 to the power 5, it's 32. So HF1 into HF2 equal to 32 into 1. So from option B is our answer. The velocity potential function phi satisfies the Laplace equation given, then the flow is how much? We know this one also already discussed. Phi exist means flow is irrotational. Flow is irrotational. And if stream function exists, flow is two-dimensional. And in this case, delta square phi exists. This is Laplace equation. So del square phi by del x square plus del square phi by del y square plus square phi by del z square equal to 0. So phi exists and Laplace equation satisfies. So flow follows continuity equation, or flow is possible. So rotational not possible, incompressible and compressible, steady and unsteady. In case of unsteady, this term will come del phi by del t, but here no del t term, del phi by del t, so it's steady flow. So this one also you can cut. Last finally C. So C is our answer. The flow is steady, incompressible and irrotational. For a two-dimensional potential flow, the velocity potential is given by phi equal to 4x into 3y minus 4 within bracket. The numerical value of stream function at point 23 is how much? Phi equal to 4x into 3y minus 4, so equal to 12xy minus 16x. This is phi value. We have to calculate stream function value at point 23. So we know u equal to del phi by del x. So u equal to del by del x of 12xy minus 16x. So we will get 12x minus 16. We know u equal to minus del psi by del y, stream function. So this is 12i dy dx of 12xy, so we will get 12y. See, 12y minus 16 equal to minus del psi del by del y. So del psi equal to 16 minus 12y to del y. If we integrate, we will get psi equal to 16y minus 12y square by 2. So psi equal to 16y minus 6y square plus constant Take it as equation 1. Next, v equal to del phi by del y. Places that v equal to del by del y of phi value 12xy minus 16x. So we will get 12x minus 0. So we know v equal to del psi by del x. So 12x equal to del psi by del x. So del psi equal to 12x del x. Both sides integrate. Psi equal to 12x square by 2. So it's 6x square plus constant. This is equation 2. From equation 1 and 2 we will get stream function psi equal to 6x square minus 6y square plus 16y. So psi value at point 2 and 3 will get 6 into 2 square is 4 minus 6 into 3 square is 9 plus 16 into 3 24 54 plus 48 minus 30 plus 48, so 18 units. Psi at stream function at point 2, 3 equal to 18 units. So from option C is our answer. The specific weight W of ocean water changes according to the equation W equal to WO plus C root H, and W equal to specific weight of ocean water at free surface, and C is a constant. The pressure at a function of depth H is how much? Here given W equal to WO C root H, and we know del P by del H equal to rho G. This is Pascal law. Here del P equal to rho G del H. If we integrate this one, and rho G is specific weight to del H, then we will integrate this one. So P equal to integration of WO plus C root H whole into dH. Then if we integrate, then WO is constant to integration of dH, H, C is constant, H to the power 1 by 2 plus 1 by 1 by 2 plus 1. So W into H plus 2 by 3 C into H to the power 3 by 2. P equal to WH plus 2 by 3 C H to the power 3 by 2. This is our answer. So from option W into H 2 by 3 C H to the power 3 by 2. C is our answer. Thank you friends. Thank you for watching my video. If you like my video, then subscribe it. Thank you.